Welcome to this explainer. Today we are going on an absolutely incredible journey. We're going to take a single, totally invisible rule of physics, something you have probably felt in your own body, and we're going to track it all the way from your local ice rink, down the highway, into a high-tech laboratory, and finally way out to the very edges of the universe. Okay, so let's dive right into this by anchoring ourselves to a super relatable, everyday phenomenon. We have all seen a figure skater pull their arms in and just suddenly turn into this high-speed human blur. Or, maybe you've sat on a spinning office chair, held heavy weights out, and then tucked them into your chest, only to feel yourself whipping around faster and faster until you're completely dizzy. So why does that actually happen? It's definitely not magic, and they aren't pushing off the ground to gain more speed.
The secret here lies in let's call it the oomph of rotation. In physics, the amount of rotational oomph a system has doesn't just depend on how heavy it is or even how fast it's spinning. It depends really heavily on exactly where the mass is distributed relative to the center or the axis of rotation.
So think about it like this. When you have your arms outstretched, your mass is far from the center. Physicists call this having a high moment of inertia, which basically just means it makes it harder to spin. But when you pull that mass in closer to your body, lowering your moment of inertia, the universe essentially demands a trade. To keep the total amount of rotational energy perfectly balanced, your rotation speed literally forces itself to increase.
Now, instead of getting bogged down in dry math and complex variables, let's just intuitively define this fundamental physical law. It's called the conservation of angular momentum. In a closed system, the total rotational oomph just stays constant. If you shrink the radius of the spinning object, the speed of the spin has to increase to compensate. It is a strict, unbreakable rule of nature.
Well, here is where things get really fun. Because if a figure skater can harness this energy to spin faster, we've got to ask, could we scale this up to solve everyday engineering problems? Like, could we use this exact same physical law to power our cities, or even the vehicles we drive?
Think about driving down a steep mountain. Every single time a car slams its brakes, it just heats up the universe. You're taking millions of joules of forward linear kinetic energy and basically just throwing it away as friction and heat. But what if, instead of brake pads rubbing together, we used a device called a flywheel? A flywheel is essentially a heavy disk that temporarily stores that linear kinetic energy as pure, high-speed rotational energy.
And looking at this concept, it brilliantly illustrates that this isn't just science fiction. The U.S. Department of Energy has actually seriously studied mounting these flywheels under cars. The idea is, instead of braking, you transfer the car's forward motion into the flywheel, spinning it up. Then, when the light turns green, you tap right back into that spinning momentum to accelerate the car again, without burning a single drop of fuel. Pretty amazing, right? To see the extreme scale of this in the real world today, we just need to look over at the MIT Magnet Lab. They use two colossal flywheels to power their experiments. Each one of these solid steel discs weighs a staggering 85 tons. That is 85,000 kilograms, and they're spinning around 6 times every single second.
These massive rotors store unbelievable amounts of mechanical energy. We're talking a whopping 200 million joules each. When scientists there need to run an experiment, they don't just plug into the city grid. They dump all that stored rotational energy into incredibly strong magnetic fields in a matter of just 5 seconds. It is a spectacular example of harnessing the spin.
So we've talked about human bodies and giant metal disks. But what happens when the universe itself decides to build a flywheel out of the remnants of a dying star?
About 5,000 light-years away from us, in the Crab Nebula, there is a neutron star. It was born from a massive supernova explosion that was actually observed on Earth back in the year 1054. Now, this star packs the entire mass of our Sun into a sphere with a ridiculously small radius of just 10 kilometers. That's roughly the size of a single city.
Remember our skater pulling their arms in earlier? Well, this star used to be massive, but it collapsed violently inward. Because of that exact same conservation of angular momentum, bringing all that mass into a tiny 10-kilometer sphere means it now rotates at a mind-boggling speed. This entire ultra-dense star completes a full revolution every 33 milliseconds. That's roughly 30 times a second.
Just look at this recent image from the Chandra X-ray Observatory. It captures the immense, chaotic beauty of this pulsar perfectly. As it violently spins, it's just blasting out copious amounts of X-rays and these massive jets of ionized gas across light-years of space.
The energy output we are looking at here is phenomenal. This tiny,
10-kilometer spinning top is generating roughly 150,000 times more power than our entire sun. But you can't get energy from nowhere, so who is paying the cosmic energy bill for this spectacular light show?
Okay, here is the most fascinating part of this entire explainer. Astronomers have precisely measured the star's spin and found it's actually slowing down by 36.4 nanoseconds every single day. And when you calculate the kinetic energy lost by that tiny slowdown in its spin, it exactly matches the colossal energy radiating out as X-rays. Every single ounce of that brilliant energy is paid for purely by the star slowing its spin down. At this current rate, it's estimated to coast to a complete halt in about 1,000 years.
So we've seen this law govern human bodies, giant metal wheels, and massive, super-dense stars. But remarkably, the universe demands that this rule apply absolutely everywhere. And yes, that means it also rules the invisible, subatomic world.
When we zoom way down into quantum mechanics, we have to distinguish between two things. First, there's orbital angular momentum, which is a particle actually moving around an axis through space. But then, there is intrinsic spin. This is an unchangeable, fundamental characteristic built right into the fabric of elementary particles, like electrons.
Now to be clear, a subatomic particle isn't a literal tiny spinning ball. The physics is actually a bit closer to a wave circulation, but the math and the physical reality, they are identical to our skater. Particles possess intrinsic spin, and their total angular momentum remains strictly conserved, even in the absolute chaos of the quantum realm. Interactions transfer momentum back and forth perfectly without dropping a single fraction of an ounce of that rotational oomph. It all comes back to that one simple, highly elegant rule. A skater pulls their arms in, a star collapses, a particle exists, and the spin is perfectly preserved. I'll leave you with this final thought to ponder. If the breathtaking, interconnected mechanics of our universe apply the exact same law to an invisible electron as they do to a dying star, what other universal secrets are hiding right in front of us, just waiting to be explained?